Just a very quick intro before the real intro. This is a second version of this video. I recently uploaded a similar one, but there was a mistake with the diagram, and actually today we also got support for U-boot, so I decided to re-record with U-boot in mind, so hopefully you will get even a better video this time. Welcome back to My Geeky Hobby. Today we are looking at a little bit of a newer piece of technology. On My Geeky Hobby YouTube channel, we don't discriminate technology based on its age. So for a change, we're looking at something brand new. A couple of colleagues from work decided to do a group purchase of a new Linux board, a small single board computer based on Risc-V architecture. So I jumped on a bandwagon and decided to contribute and also get myself one of those single board computers for some experiments on a rather new technology. So what is an interesting fact about this new board, besides the fact that it's based on a processor with Risc-V, it's a single chip solution. So the whole unit is based on just one main chip. It's the Buffalo BL808 chip, and inside the chip are not just the Risc-V CPUs. There's actually 3 of them on this board, but there's also a radio module that supports Wi-Fi, Bluetooth, and Zigbee. So it can end up being a very interesting alternative to other single board computers that are currently on the market. Let me just quickly show you roughly what's inside. So that's the internal architecture of the processor or the system on a chip that is used in this board. And listed here are 3 CPUs that are inside this system. So today, I'll show you the module, and we'll try to get Linux booting on it. So what I have on the desk is actually 3 different units. We have the Pine64, Ox64. We have the Raspberry Pi Pico. And we have a Raspberry Pi Zero. So where is our Pine Ox64 falling into? I mean, physically, as you can see, it's very similar to Raspberry Pi Pico. But in terms of functionality, it's actually closer to Raspberry Pi Zero. Why? Because it is a system on a chip. It is actually capable of running Linux. So both Raspberry Pi Zero and this Ox64 will happily boot Linux operating system. Pico, I don't think I've seen it in use with Linux yet. And I think it's missing a memory controller to really be able to, or to be capable of running Linux. Obviously, the good thing about the Ox64 is that you can get it. Raspberry Pi Zero is probably easier to get than a Raspberry Pi 4, but it's kind of hard to get it. Let's take a closer look at the two units, Raspberry Pi Pico and this new Ox64. As you can see, physically, they look extremely close. I mean, you could, I mean, if not the color, you could mistake them. Good thing about Pico is that there's no components on the bottom side, which means you can solder it on top of another PCB. This one has got the card socket at the bottom, so it doesn't sit flush with a PCB. But connectivity-wise, it looks very similar. It has the same number of pins. Obviously the pinouts are going to be slightly different, but those units are kind of similar. So looking at our Ox64, that's the board. There's a couple of elements, couple of obvious elements on the board. We have we see the main chip, the SoC, the BL808 SoC. There's some external SPI flash memory. This unit came with the 128 megabits of flash memory installed, so that's the version that you buy with that size of the flash memory. Flash memory is in a rather large package, so it should be relatively simple to change it if needed. There's a boot button where you can press it during power on to put this module into a special firmware download mode. There's an onboard DC to DC converter for powering of the SoC, and the only other thing is a small antenna that is used for the Wi-Fi, Bluetooth, and Zigbee. Built into this SoC. At the bottom of the board, we see the socket for micro SD card. And that's about it. There are two USB ports. The one on the right hand side is not connected to anything internally. It's only used for providing power to the unit. The one on the other side is a USB-C port, and that's obviously plugged into the or connected to the SoC. I'm recording this in 2023 in February. At this point of time, the drivers for the Wi-Fi, I haven't seen them available yet, so kind of early days. Last thing I haven't mentioned, there's a JTAG header, obviously some non-standard size. It's not 0.1 inch as we see the rest of the pins. There are labels at the bottom, but they are really tiny for all the pins, very hard to read. I consider them pretty useless. So that's the board. Small status LED as well here that I'm just noticing. That's about it for the actual hardware. Okay, so the next thing is obviously if we want to start using this module, we probably want some headers soldered onto those contacts. So the question first would be, do we want the headers on top side or do we want the headers on the bottom side? As you can see on top side, it's gonna be tough. That memory is in the way. You might think, oh, it would be nice to have it on top side because there are some labels. The ports are labeled at the bottom, but just compare my nails to these labels. Those labels are so tiny, they are pretty useless. So we don't really care. I don't believe there's enough space to solder the stuff at the top. So the best place to put the headers would be at the bottom. And that's what we're going to do. We're going to try to install it at the bottom. To aid the actual soldering process, let's stick those headers. Those are 20 pin headers. Let's stick those headers into a breadboard, and that will serve as a base, and it will keep our module stable. We want to get the soldering iron nice and hot, and let's get this nicely soldered. I'll start by doing like just one pin on each side, just to keep it a little bit more steady. Like that. And now we can do the rest. I'll try to bring you a bit closer. Okay, that's it. The headers are nicely soldered. We can use some isopropyl alcohol to clean up the flux from this soldering job, but I'm happy with this. That's done. Okay. So now that we have our module soldered ready to go, we obviously need to somehow connect it to the computer. If we head to the Pine64 wiki, they have the process roughly described there. There's a bit of a discussion about compatible serial ports. So if you scroll down to the section where it says compatible UART, you will see that they specifically mention a couple of different solutions for connecting. Part of the complication is that at some point you will need a UART that is running at quite a fast speed. It's 2 million baud, so not all your typical cheap serial ports support that speed. And you also need really two serial connections, one for flashing the firmware and one for interacting with the Linux shell. What I would recommend is using another small computer or small module, which is the Raspberry Pi Pico. We can load it up with some firmware and make it act as our serial port. So what I've actually done is on this wiki, this second link here leads to my GitHub repository. And on that repository, you have a connectivity diagram between the Ox64 and Raspberry Pi Pico with all the connections that are required. The Raspberry Pi Pico in this case will also provide power to our Ox64. So you connect it this way, and what will happen is once we program this Pi Pico with dedicated firmware, and plug it to a computer, the Pico will show up in the computer as two serial ports, and it will allow us the communication in and out of the Ox64. In the repository, there's this Pico probe UF2 file. This is what you need to load into the Pi Pico to make it act as a serial port. So we'll try to do it now, and I'll show you quickly how it's all done. So first of all, obviously head out to my repository, download this file. This is the precompiled file ready to go. The next thing you need to do is you need to put obviously you need to make the connections according to the diagram, but you also need to start by putting the Pico into a programming mode. So you hold the boot button, you then plug the module into your computer, and what you'll see, I mean, on my computer, it opened up as a folder. You to my screen, so you see the Raspberry Pi Pico opened as a USB drive, and I'm simply gonna drag and drop the firmware onto that drive. What this does, it restarts the Raspberry Pi Pico with the new firmware. And now in my device manager, you see I've got two brand new serial ports. So that's my Raspberry Pi Pico pretending to be the serial port. So in my computer, those two ports were enumerated as COM7 and COM9. So you got the lower port and the higher port. For the connectivity diagram, the way I showed on GitHub, port 7 is going to be our Linux shell port, and port 9 is going to be our programming or firmware programming port. So that's the two important pieces of information. In terms of the actual connectivity to those ports, you need some software to make this connection. I'm using PuTTY, so simply select PuTTY from this selection here. Select serial port, and then you select which serial port you want to talk to. So we'll be testing first this this module without any additional firmware, so just brand new as it comes, factory new, which means that we need to connect to our COM port 9, and the speed is in this case 2 million, so it's 2 and 6 zeros. So if we open the port this way, we will see exactly what comes out, or we'll see as the device boots. So let's try that. Okay, so we're ready to power up. We've got the serial ports plugged in. Let's get the power plugged in and see what happens. So as you can see, this is the initial boot of the unit. So this unit has not been programmed yet. And all it's doing is just, sending this ping pong messages just to report itself on the serial port. That is the serial that is used to program it. So that's not the actual Linux shell serial. So that's the serial that we're going to be using to update the firmware of the unit. Okay, so to get us with working Linux on the device, we need a couple of things. The full instructions of how to program the device are on this GitHub. I'll put descriptions. I'll put the links in the description. The exciting part is that today we have actually a new release that supports U-boot as well. So hopefully the whole process is going to be much easier in the future, where you only need to change the files on the SD card. But if we follow this instruction here, what we need is a piece of software called DevCube, so that it will help us, or this software will allow us to program the firmware. We also need another piece of software called Balena Etcher, which will allow us to program the SD card on the unit. So this is the two pieces of software. And the actual firmware that we're going to be programming is from this GitHub repository. So you can go to the releases and you will see that there's a brand new release 1.0 that is there. So on the releases, from the releases folder, just download this file, this tar.gzip file. So I downloaded all of those files to my computer. Most of them come already zipped, so you need to unpack them somehow. I'm recording this on a Windows machine, so I'm using 7-zip to unpack all the files. So let's do that. So first of all, I'll unpack the software that is used to do the programming. So I'll just extract it here. So that's one thing. And the other thing you need to extract is obviously the release, the actual code. So I'll extract it here as well. This gets extracted, but it's actually, there's another zipped file inside. So you need to extract that one as well. And after extracting, you will see that inside this firmware folder, there's a couple of files. 3 of them are to be programmed through a serial port. And the 4th one is an image of the SD card. So let's deal with them one by one. Of course, like I said, we're going to be following these instructions. If you had already a serial communication open to your module, you want to close all the standalone serial communication with the module, so the port is available for the software. So what we're going to do is we're going to start by running this DevCube software. So double click to open the software. Select BL808 module or SOC. And this software comes with this GUI as a couple of options to select here. It's very simple in terms of what you need to follow. It's pretty well instructed here, but ultimately we will start by going into this MCU tab. Okay, and we have a couple of selections to do. So according to this instruction, we need to select group 0 for both of those. Addresses, the first address for the M0 is already specified in this software. The second address, we'll just steal it from here. Go back to here. Okay, now we need to select the actual files that we're going to be programming. M0 and D0 are the actual Risc-V CPUs or Risc-V CPUs. So we are going to the firmware folder and we need to select the correct one. So for the first one is the M0 file. For the second one, it's the D0 file. Okay, so this is selection of the different files. Now, how we're going to program? We're going to program over the serial connection. So we're going to select COM port 9, the higher port number in your computer. It defaults here to 2000. I've struggled, I was getting errors sometimes when running at 2 million. So I'll change it to 1 million. It's still fast enough to run it at 1 million, but it will guarantee that we don't have errors this way. So with all those selected, you just hit create and download. And we get an error. Okay, so with all those selections made, there's obviously one crucial thing that you need to do is you need to bring your Ox64 into a programming mode. So similar to what we've done with the Pico on the Ox64, there is this boot button here. You just press and hold it, and whilst you're holding it, supply the module with power, and that will bring the Ox64 into programming mode. So it's now ready to accept the connection from the software. So back to the software, we can now hit create and download. And you can see it will try to synchronize with the module, and it is programming. Okay, so that's successful. The next thing we need to do is go to this IoT tab in here. Same thing. Let's get the instructions because we need to make sure that we select the correct address. So we're going to enable single download option. We're going to specify the start address and we're going to grab the file. So once again, we go to our firmware folder. And in here for this Pine64, we're going to select this firmware. Like we did before with the UART, we need to configure the UART. So 9, and I'll change this to 1 million instead of 2 million. The module is still in a programming mode, so you don't need to do anything else. It should be now just a case of hitting create and download. As you can see, it's synchronizing. It will erase the flash and it will program itself. Okay, programming. It will do probably some CRC checks or checksums. It will verify the checksums to confirm that it's programmed correctly. Okay, so that's it in this software. So we got 100% all good. We can close this software now. So the last thing that we need to do is to program the SD card. So grab yourself an SD card. I'm using a 32 gig SanDisk and a small USB card reader. So on the computer, you simply start the Balena Etcher software. Then you select the image file that you want to write into the SD card. So in the firmware folder, you will see this SD card full image. You can select that. I'm selecting obviously my SD card. Be careful, don't accidentally select your main hard disk because you may override your own files. So just make sure you've got the right selection here, and then you hit flash. When you hit flash, it will start programming. I'll speed this part, speed it up for you, but ultimately that's gonna now write the image into the SD card. And we can close this software. So now we can take the card into the module, make sure that it's facing pins up, and it just goes into the socket just under the connector. Okay, so with all of this plugged in, exciting moment, we can now try to start this module. Everything should be ready. It should boot into Linux, obviously. Remember, we have 2 serial ports, so now we're going to connect to the other serial port, which in my case is COM port 7. We stick to the 2 million baud speed because that's what the device is programmed to boot at. So we actually need to use that speed. So with all of this, let's see Linux booting. I'm just going to plug the power in. As you can see, the first thing you will see is U-boot actually booting. That means that in the future, hopefully, we don't have to mess around with the firmware too much. And U-boot is going to load the rest of the files for us. We're at the login prompt. The default username is root. There's no password. That's how quickly Linux booted on this device. So we loaded up uname -a. You can see Linux for Risc-V loaded, df -h. That's the content of the file system. You can see it's been expanded to the full size of the SD card. So that's ready to go. I'm just quickly going to reboot it just to show you the real speed, how quickly it boots. Obviously, there's a 5-second pulse to give you an option to get into U-boot. But apart from that, it's seconds and we're in. So that's how exciting this thing is. Of course, the big thing that we're missing at this point of time, it's early March, first days of March 2023. We're still missing the Wi-Fi drivers, so there's no networking in this on this module at this point of time. But I'm pretty sure it will come soon. So subscribe. I'll try to bring more. I'll try to follow the developers who are, by the way, doing an amazing job getting us all this open source software up and running. I'm sure they're going to get the Wi-Fi thing working pretty soon, and we can take the full advantage of this fantastic Linux-based module. So that's it for tonight. I hope you enjoyed. Thanks for staying with me, and thanks for watching the video. I'll see you on the next one.